Hello guys, and welcome to the grand finale of the contour integration series on this channel. If you guys have watched all the previous videos, or maybe you're watching this all as one video, I thank you very much for all the support of the channel, and I hope you really learned a lot about contour integration, and hopefully after this video you'll be ready to use it for whatever it is you are trying to solve. So again, thank you all for all the support, and I hope you enjoyed this series. Anyway, let's go over what we're going to cover in this video. We're going to cover common contours that we use for integration, symmetry, bounding, and branching, which is three important criteria that we use to decide what type of contour we're going to use to integrate. We're going to cover how to choose what kind of contour you're going to use to integrate and how to modify that contour so that it fits your exact needs for that exact function and that exact integral. So without any further ado, let's jump right into it. This is going to be a more fun video, so let's go ahead and get started. So first, I'm going to go over the contours that are covered in this video. We will be covering the semicircular contour, the circular sector contour, the keyhole contour, the circular contour, and the box contour. Now there are some contours that we won't cover because they're a little bit more advanced or they're just not useful for our purposes. So the Hankel contour, which is used in complex analysis, the dog bone contour, which is used when you have multiple branch cuts that run in opposite directions, the T-bone contour, which is for similar situations, and contours involving residues at infinity. Now, we did not cover residues at infinity, so I'm not going to be discussing those contours, but if you would like to learn more about contour integration after you finish this video, I definitely suggest searching up some of these contours and figuring out how to use them in integration. So let's go ahead and get started. The first thing we want to cover is how do we choose how to create a contour? And essentially, there's three things that we should be considered when we're choosing a path for our contour integral. The number one absolute most important is symmetry. If our function has some symmetry along some line or curve in the complex plane, use that to your advantage in order to close your contour. This is typically ray symmetry or parallel symmetry. Now, what we mean by ray symmetry or parallel symmetry is essentially if you have multiple lines that come out from the origin that have some sort of similarity on them. So, for example, if your function acts very similarly on the line running from x equals 0 to positive infinity, and it looks very similar to that on the line from x equals 0 to x equals I infinity, then you should probably be using that symmetry to your advantage in order to close your contour, because, of course, we want to make evaluating a contour integral as easy as possible, and so that means we need to make sure that as many parts of our integral as possible are going to be easy to either evaluate or to turn into a form that's already evaluable or prove that they go to 0. So that leads us into our next important topic, which is bounding. So you want to make sure as many parts of your contour as possible go to 0, because that means less sections you have to evaluate. So you'll see that some of our contours will purposefully spend a lot of time looping around close to infinity, because close to infinity in general our functions will go to 0. And then that makes our contour integral much easier to evaluate. And branching. So sometimes we'll have to modify our contour or choose one specifically due to branch cuts in our function, and that'll make a little bit more sense once we get to some of the other contours that we're going to cover in the video. So let's go ahead and get started. So the absolute go-to is the semicircular contour. This is by far the most useful contour that shows up in all sorts of situations. Now this contour just looks like a big semicircle. I have two contours here, the green one, which is the semicircle in the upper half plane, and the red one, which is the semicircle in the lower half plane. So depending on the value of your function in the upper and lower half plane, you might want to choose the upper half plane or the lower half plane. Again, you just want it to go to 0 on this outer arc right here, so you may have to choose either the upper or lower. And this is generally used for the integral from negative infinity to infinity of f of x dx. Now let's talk a little bit more about the motivation of this. So obviously, right, we have our real axis integral right here. We absorb all the residues right inside the contour, and if our function goes to 0 on this curve capital gamma right here, then our contour integral is really easy to evaluate, and that's kind of the point of choosing the semicircular contour. So it's incredibly simple, and if the function decays at infinity, then the gamma integral may go to 0. It also contains all the residues in the upper half plane or the lower half plane if you're using that version of the semicircular contour. Also something to note, if you put your semicircle in the lower half plane, then the contour you use will be oriented negatively, which means that you'll have to take into account the fact that when you use the residue theorem, you'll get negative the value of your contour integral because of the negative orientation. And the types of functions that this works well with is rational functions, trigonometric functions, logarithms. Of course, you will need to make some modifications due to the branch cut, and any bounded function in the upper half plane. So basically any function that's bounded in the upper half plane, you can go ahead and just plug in this contour and it'll work out very nicely. So in general, we're going to use a lot of rational functions with this, but here are some examples. P of z over q of z just means a rational function of z. And then when we multiply by e to the iz, that allows us to incorporate some trigonometric functions in there. And again, it's just really, really helpful because those trigonometric functions, or rather not the trigonometric functions themselves, but e to the iz is bounded in the upper half plane. Natural log of z and inverse tangent of z also works quite nicely. So let's go over a quick example for a very, very simple function. So I'm not going over every single part of this contour integral because in the past video you guys learned how to do many of the methods that I'm showing here. So if you guys want to go ahead and prove these things, then please do, right? So the example we're doing here is the integral from negative infinity to infinity of cosine of x over x squared plus 1 dx. Now, of course, we want to convert everything into a nice little complex analysis form, so this is going to be the real part of the integral from negative infinity to infinity of e to the iz over z squared plus 1 dz. So we're going to use a contour integral of the same function, and we're going to just use the upper semicircular arc. And this is really nice because we capture this residue at z equals I. We have on the real axis, this will be equal to our original integral, or rather, I guess it'll be equal to, so it'll be equal to our this integral right here on the inside of the real part function. And then on this upper semicircle, we can use Jordan's lemma in order to show that it goes to 0. So we know that the contour integral overall is going to be 2 pi I times the residues of f of z, where f of z is this function, at z equals I. And it's also going to be equal to our integral over the real axis, which we call I, plus the integral over gamma. And you guys can go ahead and show that the gamma integral goes to 0 using Jordan's lemma. And this means that 2 pi I times the residues equals our integral over the real axis, which also equals this integral right here because the imaginary part is going to be 0. So see, in just one slide with some very, very straightforward methods that you guys already know how to do since I taught you them in previous videos, we have proven this absolutely crazy integral, which would be very, very difficult to solve with any other method except maybe the Laplace transform, but even so, that would take quite a few steps to be able to solve. So that's the appeal of the semicircular integral. It makes contour integrals incredibly easy. Another integral, or another contour that we may use here is the circular sector contour. So notice that we sort of trace out the integral from 0 to infinity, and then we go back in this semicircular arc, but we won't necessarily make a full semicircle here. That depends on our value of theta. If theta equals pi, then we just get our semicircular integral, which means that the semicircular integral is actually a special case of the circular sector contour. And notice that theta can be anywhere, anything from 0 to 2 pi, and this can give us a lot of different options for our integral. And this is typically used for the integral from 0 to infinity of f of x. Now, the main appeal of this type of contour is if your function has some sort of radial symmetry, and you'll see what I mean by that. So, so it's appealing when we have power functions of z, and the reason for this is because if f of z is z to the p, then if we replace z with z times e to the 2 pi I over p, we get f of z again. And what this means is when we're replacing z times e to the 2 pi I over p, that means that the values of the function over this line will be the same as the values of the function over this line, since all we're doing is multiplying everything by e to the I theta, which in this case theta could be 2 pi over p, right? And so the appeal of this is that when we parameterize the path back from the circular arc, our integral can be expressed in terms of the real axis integral I. So this works well with rational functions, power functions, and logarithms. So here are a few examples of different functions that we can use. Again, not too many examples, but as it gets more complicated, you can figure out some other examples there. So here's a quick classic example. If we wanted to calculate the integral from 0 to infinity of 1 over x cubed plus 1 dx. Now, if this were 1 over x squared, we would just go ahead and say, okay, well, 1 over x squared is an even function, so we can write this as 1/2 the integral from negative infinity to infinity of 1 over x squared plus 1 dx. But because it's x cubed, we can't do that, and that means we can't just use our semicircular integral. So instead, we notice f of x is the same as f of e to the 2 pi I over 3 times x. And again, here we can't switch this to the integral from negative infinity to infinity, which is very, very sad, but we can use this circular sector integral. So if we consider the contour integral over the circular sector of 1 over z cubed plus 1 dz, we have this I1, this I, we have a pole at z equal to e to the pi over 3, and we have this gamma contour, of course. So the integral of f of z dz is going to be the 2 pi I times the residue at that point, and it's going to be equal to our integral I, which is the integral over the real axis, plus this integral over I1, plus this integral over gamma. And using the methods that I taught you in the last video, you can show that the integral over gamma goes to 0 using the estimation lemma. You can show that the integral I1 turns into negative e to the 2 pi I over 3 times I using parameterization. And so this means that I times 1 minus e to the 2 pi I over 3 equals 2 pi I times the residue at this point, right? And so then all you have to do is some simple algebra and analysis to get to our answer of I. So our next contour is a little bit interesting and it looks a little silly. And this is the keyhole contour. So the keyhole contour is principally for when we have a function with a branch cut. Running from the center right here all the way out to infinity. And what we do is we integrate just above the real axis. We go in a full circle all the way around in this large gamma contour. Then we come back just below the real axis. And then we go around in a tiny infinitesimally small circle right here around the point z equals 0. And essentially what will happen in many situations is because we have our branch point at z equals 0 and our branch cut running from z equals 0 to z equals positive infinity, this integral on the just above the real axis and just below the real axis are going to interact with each other a little bit. Typically they'll just be off by a factor, or they'll just be subtracting. They'll be off by like a single term, and so since they're running in opposite directions, we're going to subtract them from each other and we'll get a much simpler integral. And so the appeal of this is, whenever we have a nice little branch cut right here, this keyhole contour is really nice because it completely avoids that, and it still gives us this nice circular action, which allows us to not have too many parts of an integral that we need to evaluate. So pretty much it's the go-to contour for when you have a branch point at z equals 0 and your function is not super simple, because if it is super simple, chances are you can just use the semicircular integral. So the contour is closed, it avoids all the branch cuts, and both straight line integrals are infinitesimally close to the real axis, which means that the argument along the entire upper integral is 0 and the argument along the entire lower integral is 2 pi because of that branch cut that we place right there, which usually will lead to some nice symmetry, and I'll show you an example of that in a moment. Now, this trick is a little bit confusing, but we have what's called the phantom log trick. And what we can do is we can multiply a rational function or even a function with natural log of z in it by natural log of z, and then we integrate over the keyhole contour. And what happens is on the upper keyhole contour, natural log of z will just turn into natural log of x. But on the lower contour, natural log of z will turn into natural log of x plus 2 pi I. And then when we subtract these two integrals from each other, the natural log of x will cancel, but the 2 pi I will remain. And what this means is that essentially, once we multiply by this natural log of z, it ends up disappearing and being replaced with the 2 pi I. And so this allows us to integrate a lot of different functions over this keyhole contour. And even if these functions don't have any nice symmetry, or maybe they have singularities on the real axis, the keyhole contour is just the only place where it's going to be easy to integrate them. And it's a little bit hard to explain the phantom log trick, but if you're really stumped, you can always try multiplying a function by natural log of z and integrating over the keyhole and seeing how things cancel, and it may just work out for you. And in general, the keyhole is going to work with anything that decays to 0 as r goes to infinity and has a single branch point at z equals 0. If it has another branch point somewhere else, the keyhole contour won't work out very well. So here's an example right here. We have a pretty straightforward function, integral from 0 to infinity of z to the p over z plus a times z plus b, which is going to be equal to I, and a and b are greater than 0, p is between negative 1 and 1. So this is our keyhole contour right here. Z is we have poles at z equals minus a and z equals minus b. I don't know why it says positive here, but I didn't really draw the keyhole too well here, but it's the same as this keyhole right over here. The exact same contour. And then the point here is we get that our integral is going to be 2 pi I times the sum of the residues, and it's going to be equal to I1 plus I2 plus our lowercase gamma integral plus our uppercase gamma integral. And both of the gamma integrals go to 0 using the estimation lemma, which you can go ahead and prove right now if you want. And then when we use parametrization, we find that I1 is just going to be equal to I, and I2 is going to be equal to negative I times e to the 2 pi I p, which means that once we calculate the residues, we just need to divide by 1 minus e to the 2 pi I p, and we get the value of I. So this next one is very different from what we've seen. We've seen a lot of nice little circles and symmetry that way, or functions that go to 0 just because we have that nice circular arc. But this is going to be a go-to when functions don't go to 0 on that circular arc, and they have other types of symmetry, which we'll discuss. This is the box contour. So with the box contour, we're running from negative r to positive r, which is pretty much just going to be negative infinity to positive infinity. Then we go upwards on the imaginary axis, or not on the imaginary axis. We go upwards in the imaginary direction to plus r plus k pi I to minus r plus k pi I, and then we close the contour back down. Now, I'll go ahead and try to explain the appeal of this contour. It's a little bit confusing, but as you might expect, the key word here is symmetry. The exponential function, and by extension trigonometric and hyperbolic functions, have nice symmetry across parallel lines shifted over by 2 pi I. And this means that e to the 2 pi I, because e to the 2 pi I is 1, if we shift our function over by 2 pi I, and our function is completely composed of just e to the x, it's just going to be the same exact function. And sometimes we'll shift it over by pi I instead, because e to the pi I is negative 1. And so this means when we're using exponentials or hyperbolic functions, which don't go to 0 as r goes to infinity, the only way to close the contour is using these nice lines, because otherwise we'll just end up with some other integral that we have to solve with whatever path we take to close the integral, right? The integral, or the contour has to be closed in order to use the residue theorem, and the only really good way to close the contour is to use some symmetry so that we can combine the path that we use to close the contour with our original path. So the way we do this is we try making a big box where the top and bottom paths are k pi apart in the imaginary direction. Depending on your function, k may be 1 or 2, and even in some cases 1/2, maybe even like 3 or something like that. I don't really know how that would be helpful, but yeah, so that's the idea behind that. You can experiment by plugging in different values of k to see what gives you nice symmetry. So just plug in different values of z plus k pi I to see what gives you symmetry in your function. So here's a quick example right here, very classic example right here. We have the integral from negative infinity to infinity of e to the ax over e to the x plus 1 dx, where a is between 0 and 1. So we end up with a contour integral, and we're going to be going over the box contour. In this case, our k is equal to 2. So we just have this big box, go up by 2 pi I, go all the way back to negative r, and then go down by 2 pi I again. And we have a pole at z equals I pi, because e to the I pi equals negative 1. So, of course, our contour integral is just going to be equal to the residue at pi I, and it's going to be equal to c1 plus c2 plus c3 plus c4. And in this case, c1 is just this line right here, c2, c3, and c4. Now, c1 and c3 go to 0, which you can prove using the estimation lemma. And then using parametrization, you find that c2 and c4 are very, very similar C4 is just equal to I, and C2 is going to be equal to negative e to the 2 pi I a times I. And so all you have to do is divide by 1 minus e to the 2 pi I a, and then you get your value of I right here. Okay, go ahead and try that one if you want. All right, so this is a little bit of an interesting one. This is very different from the rest of our contour integrals because it comes directly from a substitution rather than taking our function through the complex plane. So this is just a simple circle. That's all it is. And you'll usually see it denoted by the contour integral over the modulus of z equals r. And of course, it's assumed that you're going in the counterclockwise direction. Now this only happens in a very specific type of integral, which is when we have the integral from 0 to 2 pi of f of sine of x and cosine of x dx. And we can rewrite this as g of e to the ix because sine of x is e to the ix minus 1 over e to the ix all over 2I, and cosine of x is e to the ix plus 1 over e to the ix all over 2. Something else to note here is that this function of sine of x and cosine of x, it could just be some arbitrary function of e to the ix. In general, you'll see it in forms of sine of x and cosine of x, but I've had some situations where it's just written in terms of e to the ix. And essentially what we do here is we substitute z equals e to the ix, and we get that dz over iz equals dx. And what happens is if you actually track the path of e to the ix, where x varies from 0 to 2 pi, you find that the starting point and the ending point are the same, obviously, because e to the 0 is the same as e to the 2 pi I. But if you actually track the path, you'll find that it just follows this little circle. It starts at theta equals 0, and then it goes around in a full circle right here in the counterclockwise direction, reaching theta equals 2 pi. And that is pretty much just the definition of a closed contour in the complex plane. So this means that it's actually equal to the contour integral over the modulus of z equals 1 of g of z over iz dz. So let's look at an example of how this works out. So this is our function integral from 0 to 2 pi of cosine squared of x over 3 plus 4 sine of x dx. Then z is going to be e to the ix, and dz over iz is going to be dx. And this just ends up being the contour integral over z equals 1. And then, just using the identity with cosine of x and sine of x, we get this nice expression. That's actually not a very nice expression, but it is an expression. And essentially, you just have to simplify everything, factor the bottom, find the poles, and then plug in the residues. I'm not going to do all that busy work, but if you guys want to go ahead and try that, absolutely be my guest. So let's move on to our next contour. Oh, looks like we have reached, that is all the contours that we're going to talk about today. So now I'm going to talk about irregular contours. So essentially every problem is different, and some of them will have unique contours that don't fall into any of the categories mentioned here. So just play around with your function, look for symmetry, look for places where it's well defined in the complex plane. Honestly, like some problems, they're just going to have contours that you would never even think of, and that's okay because contour integration is, a very advanced topic. You can't expect everyone to guess, oh, what if I try this random contour? But, it's always worth a shot, just trying something. So I have an example here from QN Cubed, absolutely a brilliant YouTuber. I learned a lot of the stuff that I know from him. And I was just looking at this problem the other day, and he takes this integral from -1 to 1 of inverse tangent of x times ln 1 plus x squared over x all over x plus 1 dx. And he does some manipulations, and I was able to follow most of it, but he ends up with this contour integral that goes from like e to the I pi over 4 to e to the negative I pi over 4, and then it like goes back in a circular arc, and it's like, this is the weirdest looking contour integral ever. Like who would even think of this? But you just have to sort of look at your function, look, oh, these 2 points are on the unit circle, so what if I connect them back using a contour through the complex plane, right? So it's just, it's just practice and, trying everything that pops into your mind, because you'll never know if you might just come up with a genius idea and have to try it. And with that, we have one more topic right here. We're going to talk about modifying contours. So most contours that we're going to use are going to look pretty much similar to the ones that were shown, but they're going to have slight modifications because every function is different, and that means that every contour is going to be a little bit different. So if our path runs directly over a singularity or branch point, The only thing we really have to do in that situation is make an infinitesimally small circle to go around it. And you'll see this in a lot of different contours. I'll show you an example. If you think about the keyhole contour, that's pretty much what we're doing there. We're just having an infinitesimally small circle just to go around that branch point at 0, and that's that gamma integral right there. And another thing that to keep in mind is if your function has a nasty branch cut that's getting in your way, you can always try to deform your contour around the branch cut. And I'm going to show you an example where it looks like a really silly deformation, but it works out perfectly. And so there's always a fair chance that the integration will still succeed, even if your contour looks a little bit silly. I mean, it's always worth a shot because contour integration in general is really easy to check if your function is still going to be integrable. So let's go ahead and take a look here. I want to integrate this function f of z ln z dz. I didn't rate it here, but I want to integrate it from negative infinity to infinity, I guess, in this situation, or maybe 0 to infinity. I don't know, we'll see. But anyway, I'm trying to use this semicircular contour here, but natural log of z has a branch point at z equals 0. I've chosen the branch cut to run from z equals 0 to z equals negative I infinity because that way it stays outside of our contour. But again, the branch point right here is in the way, and we cannot integrate over a branch point. So all we're going to do is deform it. We just make an infinitesimally small circle around the branch point, and voila! Now the branch point is completely out of our path of integration. This small circle doesn't actually change the value of the integral in general. Obviously, it depends on your function, but chances are this will just go to 0 anyway. And that's all we had to do. We just had to make a slight modification right there. And the same would be true if instead of natural log of z we had some sort of pole in this situation, right? So here's another deformation that's very, very common that you should get used to. First of all, know that inverse tangent of z can be defined in the complex plane as I over 2 times natural log of 1 minus iz over 1 plus iz. And then we have, if we're trying to integrate f of z times inverse tangent of z from negative infinity to infinity, of course, and we want to use the semicircular contour right here, if we choose the principal value of the natural logarithm, then we're going to have a branch point at z equals negative I, and it's going to run down to I infinity, negative I infinity. And this really isn't in the way of anything, but as you can see here, this branch cut running from I to I infinity of the other natural logarithm right here, I mean, it slices straight through our contour, and it's completely in the way. And turns out, all we have to do is deform our contour a little bit. We literally just change the contour so that it just goes around that branch cut, which looks really, really silly. I mean, I just made it go down and then around in a circle and then back up. I mean, who would think that that works? But that's actually a contour that I used twice in recent videos because it just works out very, very nicely in the end. And so, even though this looks like a very, very silly deformation, it works out quite well. So, try every deformation to get rid of those branch cuts that are making your day insufferable, right? All right, so I believe that is everything we have to cover. Yep. That is all you need to know about contour integration to get started on working on some awesome definite integrals. So I have a lot of practice problems here because now we've basically learned everything about contour integration that we know that we need to solve these problems. So let's go ahead and do some practice. So here are the first 6 practice problems. Go ahead and pause and try them. Your goal is to pick a contour which can help you evaluate the definite integral, and then go ahead and solve for the value of the definite integral. All right, hopefully you've given those a look. Let's go ahead and try another example right here, another few examples right here. These are a little bit more difficult in general. Also, if you weren't able to figure out number 5, a nice contour for this, I would suggest trying the phantom log trick, which I mentioned earlier in the video. So let's go ahead and look at the next set of practice problems. These ones are a little bit more difficult, but I think you guys can figure them all out. Alright, hopefully you gave those problems a try, and if you weren't able to figure some of them out, I'm always open in my Discord, which you should go ahead and join, just to discuss, and to see if there's anything that I can help you out with. So, I have one more bonus problem, which I think is fun. The bonus problem is to find a definite integral, which can be evaluated using the Pac-Man contour right here. I do know of a function that can be, a few definite integrals actually, which can be evaluated using this Pac-Man contour, so go ahead and give that a try if you like. But if not, thank you so much for watching my contour integration series. It has been an absolute pleasure to be your teacher, and I hope you continue to watch videos on my channel if you find them helpful. Thank you so much for watching. I hope you learned something. I'm always happy to help, and yeah, hope you enjoyed the video, and I'll see you next time.